I was going to get up here to introduce Ian May, my vice president, and I was given a slide to do it, I guess. So I'd like to introduce Ian May, my vice president of the ASME student section.
Okay, so as stated, I'm the vice chair of the ASME student section, if you didn't need to hear it 3 times. I'm also an undergraduate researcher in the Cardiovascular and Biofluid Mechanics Laboratory here at CSU. Now, I actually know very little about cardiovascular mechanics. What I do is actually pure theory on turbulence. So, one of the overarching questions that we have is whether every turbulent flow is somehow the same at the smallest scales of motion. Now, we seek to answer this question through the idea of a local Reynolds number. So if you recall, a Reynolds number measures the balance between inertial and viscous forces in a flow. However, when you look at them in practice, you see numbers like 2,000, 10,000, 100,000, and the reason that these are so, well, I shouldn't say useless, but a little bit arbitrary, is that we don't know how to choose a velocity scale, a length scale, appropriately. So instead, what we decided to do was zoom into the flow, and let's just have it always be 1, right? So if we stand at one point, we just look at the velocity there, and then we can pick a direction, and we can move that way, and simultaneously keep track of how far we've gone and the velocity difference that we've built up in that time. And from that, we can construct this local Reynolds number. If we rearrange this, we can get a description of the flow by just looking at that length scale. So in my work here, I've sought to describe this length scale through a distribution, which we can kind of see here. Now this is a very particular case. So let's kind of bring this back up to engineering flows, real-world applications, instead of just pure theory. Real engineering flows exhibit high degrees of inhomogeneity and anisotropy. For instance, boundary layer flows. Those are excellent canonical example of this. So just sort of to recall, you have your no-slip condition along some plate or some surface, and that builds this velocity profile that we see. And there's a very complex structure that arises out of this regime. And if we can describe these scales as well, then we just might have a much more full understanding of turbulence. So, as we saw in the previous talk, computational fluid dynamics has pretty significant impact on the design of current components and current systems. So what I hope to do through this research and all of this kind of heavy theory is to develop some new turbulence models, or at least modify existing ones. So for instance, many codes seek to solve the Reynolds average Navier-Stokes. And if you're familiar with the system there, the troublesome term is the Reynolds stress. But a Reynolds stress is really just a statistical quantity. So if we have a statistical understanding of these scales, hopefully we can sort of pull it back and build a much more interesting model there. Additionally, we have sort of the unknown applications. These are my favorite. I suppose that makes me a little bit of a physicist, but anytime you do some of this interesting theory work, it's kind of cool to see what someone else will do and use it for, right? Because I don't know. Maybe someone will apply this in something completely different, at least the analysis methods that we've sort of introduced here. Yeah, so that's a bit about myself and my research, but keeping with the theme of the night, I'd like to kind of move back towards ASME and our student section here. So it's been highly influential in the development of my academic character. So, as Jeff sort of hinted at earlier, you get to meet a very large number of people, and some of them can show you just what's possible. For instance, Tyler and Kevin on their project. Whereas in lectures, sometimes you just see what's adequate. It's nice to see that there's something to reach for in quality of work. You also get a look at the professional world. So I know co-ops have been mentioned tonight, internships. We try to lead a bunch of industry tours if we can. So we've toured the New Belgium plant, we've toured Woodward, Wolf Robotics, a few other pretty big names. And it also never hurts to kind of keep your life in perspective. right? So we can take a look at some of our service efforts and some of our community involvement. For instance, we will bring exhibits to these STEM nights, science, technology, engineering, and mathematics. That's really nice because the whole goal of these nights is to take basic mechanical systems and show them to, well, I guess what I can call the next generation. Feels a little weird to say that at my age, though. But just sort of through my presence in this society, it's certainly driven me to be capable of what I've done in my research. And I hope all of you look forward to the future and see what it holds just for ASME, mechanical engineering, and our society. So on that note, I'd like to turn it over to Jeff, and he will talk a bit more about ASME specifically.